Hi everybody, in this video we will begin with Chapter 12, Probability Distributions. And these are the learning objectives of this chapter. So by the end of the chapter you should be familiar with discrete random variables and their probability distributions, continuous random variables and their probability density functions, the effect of linear transformations of the random variable x on the value of its parameters, the normal distribution, properties, normal probability calculations, and inverse normal calculations, standardizing normal variables or z-values, inverse normal calculations where mean and standard deviation are unknown, and the binomial distribution, including its mean and variance. We're going to start with section 12.1, random variables. When a probability experiment is performed, we are often not interested in all the details of the outcomes, but only in the value of some numerical quantity determined by the result. For instance, in tossing two dice, we often care only about their sum and not the values of the individual dice. A sample space for which the points are equally likely is given in Table 15.1. It consists of 36 ordered pairs, A, B, where A is a number on the first dice and B is a number on the second dice. For each sample point, we can let the random variable uppercase X stand for the sum of the numbers. The resulting values of small cap x are also presented in the table. So notice that the random variable x would be the entire sample space with all the possible results of adding the two dice. And then lowercase x represents each resulting value. Notice that events can be more accurately and concisely defined in terms of the random variable x. For example, the event of getting a sum greater than or equal to 5 but less than 9 can be replaced by this inequality. We can think of many examples of random variables. For instance, the number of calls received by a household on Friday night, the number of beds available at hotels in a large city, the number of customers a salesperson contacts on a working day, the length of a metal bar produced by a certain machine, the weight of newborn babies in a large hospital. Next, we're going to focus on example 12.1. And it says, state whether each of the following is a discrete or continuous random variable. Letter A, the number of hairs on a Scottish Terrier. Well, even though the number of hairs is incredibly large, it's countable. So this is a discrete variable. B, the height of a building. Well, this can be any real number. Even when we say that the building is 15 meters high, the number could be 15.1 or 15.02 meters and so on. So this is continuous. C, the amount of fat in a steak. Well, this is continuous since the amount of fat could be 0 up to the maximum amount of fat that can be held in one piece. For letter D, a high school student's grade on a history test. Well, this is obviously discrete because no matter how detailed a score the teacher gives, the grades are isolated points on a scale. Letter E, the number of fish in the Atlantic Ocean. Although this is an unfathomably large number, it is still theoretically countable, hence discrete. For letter F, the temperature on an electric kettle. This is continuous since the temperature can take any value from room temperature up to 100 degrees Celsius or even more. So next we're going to talk about discrete probability distribution. Here's an example of the frequency distribution of 25 families in Lower Austria that were polled in a marketing survey to list the number of liters of milk consumed during a particular week. Now this was from a previous chapter, as you can probably recall. Table 15.2 lists the number of liters consumed to the nearest liter along with the relative frequency. One of the interpretations of probability is that it is understood to be the long-term relative frequency of the event. So a table like this, we replace the relative frequency with probability, and it would be called a probability distribution of the random variable. Now it is important to notice that the probability distribution for a discrete random variable is a table, graph, or formula that gives the possible values of x and the probability p of x, also written as this, associated with each value of x. This is also called the probability mass function, PMF, and in many sources it is called the probability distribution function, or PDF. In other words, for every possible value x of the random variable capitalized X, the probability mass function specifies the probability of observing that value when the experiment is performed. If uppercase X is the number of liters of milk to the nearest liter consumed by a family, the probability distribution of X is as follows. So notice that it's basically the same table, only that it is now horizontal, and the frequencies represent actually the probability of the consumption of said liters of milk. The other form of representing the probability distribution is with a histogram, as shown in figure 15.2. Every bar corresponds to the probability that is associated to the value of X. So notice that 0 is 0.8 probability that we can see here, and so forth. The values of X naturally represent mutually exclusive events. Summing P of X over all values of X is equivalent to adding the probabilities of all simple events in the sample space, and hence the total is 1. So now let's take a look at probability distribution functions of discrete random variables. Let uppercase X be a discrete random variable with probability distribution function P of X, then P of X will be between 0 and 1, including 0 and 1, for any value X. The individual probabilities have to sum 1. That is, in sigma notation, the summation over all possible values of X. For some value lowercase x of the random variable uppercase X, we often wish to compute the probability that the observed value of uppercase X is at most lowercase x. This gives rise to the cumulative distribution function, or CDF. For example, in the milk consumption case, the CDF will look like table 15.4. So notice that basically this is the same as the cumulative frequency, but this is now a cumulative probability. So f of 3 is 0.84. That's the probability of a family consuming up to 3 liters of milk. The result can be achieved by adding the probabilities corresponding to x equals 0, 1, 2, and 3. So notice that this number here is the sum of the probabilities of consuming 0, 1, 2, and 3 liters. So in many cases, we can use the cumulative distribution to find individual probabilities. This is the formula. Now, what it means is this: if you want to find the probability that x equals 3, we can use the table 15.4, and notice that the probability of x equaling 3 is equal to the probability of x being less than or equal to 3 minus the probability of x being less than 3. So in other words, it's simply subtracting this value minus the previous value. So we get 0.20. This property is of great value when studying the binomial and Poisson distributions. So next we have example 12.2, and it says radon is a major cause of lung cancer. It is a radioactive gas produced by the natural decay of radium in rocks that contain small amounts of uranium. Studies in areas with high levels of radon reveal that 1/3 of houses, so 1/3 of the houses in these areas have dangerous levels of radon. Suppose that 2 houses are randomly selected. So 2 houses are randomly selected. And we define the random variable x to be the number of houses with dangerous levels. Find the probability distribution of x by a table, a graph, and a formula. So notice that here they're telling us the probable values of x are 0 houses, 1 house, or 2 houses having high levels of radon. Also, they told us that the probability of a house containing high levels of radon is 1/3, because it says that 1/3 of the houses have the high levels. So what is the probability of x equals 2? That is the probability of finding high levels of radon in the first house, so 1 yes, and finding high levels of radon in the second house. So this is going to be the probability of the first house having high levels of radon times the probability of the second house having high levels of radon. And then this is going to be 1/3 times 1/3 which is equal to 1/9. What would be the probability of 0, of x equals 0? So that would be the probability of the first house not having high levels of radon and the second house not having high levels of radon. So notice that this is going to be the complement of this, right? Times the complement of this. So in other words, 2/3 times 2/3, and this is equal to 4/9. So what is the probability of finding one house with high levels of radon? Now, because the full event is these three probabilities, that means that this is 1 minus the other two, right? It's the complement of the other two. So 1 minus 1/9 plus 4/9. And if you do the math, this is going to give you 4/9. Now, what would have been the other way of doing this? Well, the other way of doing this would be the probability of finding radon or high levels of radon in the first house and not finding high levels of radon in the second house, or finding low levels of radon or not high levels of radon in the first house and finding high levels of radon in the second house. So this would be the second house, not the first house. And notice that this should give us the same, because this would be 1/3 times 2/3 plus 2/3 times 1/3. And this also gives us 4/9. So now let's take a look at the table. Notice that here we have the table to the left, and this is the probability distribution table for this example. So notice that 0 is 4/9, 1 is 4/9, and 2 is 1/9. If you add these, it has to equal 1. And then the graph is a histogram where in the x-axis we have the number of houses, and on the y-axis we have the probability. So notice that 4/9 for 0 or 1, and then 1/9 for 2. So notice that they ask us to find the probability of the distribution of x by table, by graph, and also by formula. So what formula are they talking about? They're talking about the formula of a binomial distribution. And that formula is this one. P of x is equal to, now this is just a combination, times p to the x times q to the n minus x. So does this seem familiar? Well, yes, right? Remember that this was the formula that we used for expansion of binomials. And what do these different variables represent? Okay, so n is the number of trials in the experiment. Then we have x. X is going to be the number of successes that we expect. And then P is the probability of success, whereas Q is the complement of this, or the probability of failure. So in this example that we're doing, N is the number of trials. There's going to be 2 trials because we're going to find out in 2 different houses, right? The number of successes, that's going to be the variables, 0, 1, or 2. P, the probability of success, that's going to be 1/3. And then Q, the complement of this, or the probability of failure, is 2/3. So our formula would then be P of x is equal to the combination of 2 and x, and then 1/3 to the x times 2/3 to the n, or 2 in this case, minus x. So let's see if we get the same results using the formula. So notice that p of 0 would then equal combination 2 and 0 times 1/3 to the 0 times 2/3 to the 2 minus 0. So this is going to give us 1 times 1 times 4/9, and this equals 4/9. So notice that we get the same answer. So the probability of 1 is going to be 2 in combination with 1, and then 1/3 to the 1 times 2/3 to the 2 minus 1. So this is going to be 2 times 1/3 times 2/3, which is going to equal 4/9. So we get the same result. And then P of 2 is going to be 2 in combination with 2, 1/3 to the 2, and this times 2/3 to the 2 minus 2. So then notice that this is going to be 1 times 1/9 times 1, and it equals 1/9. And notice that we get the same answer. We continue with example 12.3, and it says, many universities have a policy of posting the grade distributions for their courses. Several of the universities have a grade point average that codes the grades in the following manner. A is 4, B is 3, C is 2, D is 1, and F is 0. During the spring term at a certain large university, 13% of the students in an introductory statistics course received grade A, 37% B, 45% C, 4% D, and 1% F. A student is chosen at random and the grade noted. The student's grade on the 4-point scale is a random variable x. Here is the probability distribution of x. So notice that here we have x and the probability of x. So 1%, 4%, 45%, 37%, 13%. Is this a probability distribution? Well, they say it is, right? But what is the proof that it is? Well, notice that first of all, every probability is between 0 and 1. So that's the first condition, including 0 and 1, by the way. And then the other condition is that the sum of the total probabilities must equal 1. And we can see that this is also true, because 0.13 plus 0.37 would be 0.50. Then this would make it 0.95, 0.99, and then 1. Okay, how about B? What is the probability that a randomly chosen student receives a grade B or better? So that means the probability that the grade is equal to or higher than 3. So notice that this is simply going to be the probability that it's 3 or plus the probability that it's 4. And this is simply going to be 0.37 plus 0.13, and this equals 0.50 or 50%. Now we're going to take a look at example 12.4. And it says, when people choose codes for their smartphones, the first digits follow a probability distribution similar to the one below. So we saw this example in a previous chapter, but now we are applying it to probability distributions. Here, X represents the first digit chosen. What is the probability that you pick a first digit that is more than 5? So notice that that's simply going to be the probability that we choose 6 plus the probability that we choose 7, or that we choose 8, or the probability that we choose 9. So then this is going to be 0.067 plus 0.058 plus 0.051 plus 0.045, and this is going to give us 0.221 or 22.1%. Then it says show a probability histogram for the distribution. For this part, we're going to use the GDC. So this is simply going to be a histogram. We go to Stats, Edit, and then notice that I've already entered the values in list 1 for the first digits from 0 to 9, and then in list 2, the probability for each digit. So for this, we need to go to StatPlot. But before you do that, make sure you don't have anything in y equals, otherwise you will get an error. So we go second, StatPlot, make sure that number 1 is on, and then we want to choose a histogram, which is right here. That's the histogram. And then we're going to go down and make sure X list is list 1 and the frequency is list 2. The other thing we have to be careful with is the window. So notice that I have a minimum for X of 0, a maximum of 10, which is just a little bit above the 9. The X scale at 1 is fine. The Y minimum is 0 and the maximum is 0.5. That is because the maximum probability was about 30%. Then the scale I'm going to use is going to be 0.001, although I could also use 0.01. And let me just clear this out. Let's make it 0.01. And then we hit graph. And there it is. That would be the histogram for the distribution regarding the first digit of a smartphone code. So now let's talk about expected values. The probability distribution for a random variable looks very similar to the relative frequency distribution that we discussed in Chapter 10. The difference is that the relative frequency distribution describes a sample of measurements, whereas a probability distribution is constructed as a model for the entire population. Just as a mean and a standard deviation give you measures for the center and spread of the sample data, you can calculate similar measures to describe the center and spread of the population. The population mean, which measures the average value of X in the population, is also called the expected value of the random variable X. It is a value that we would expect to observe on average if we repeated the experiment an infinite number of times. So basically, the expected value is simply the population mean. So in the next slide, we revisit the milk consumption example. And here is the table of probabilities. Now, suppose that we have a large population or number of families, let's say 100,000. So using the relative frequency concept of probability, we would expect to observe 80,000 families consuming no milk. That is simply 100,000 times 8%, right? For 1 liter, we would have 20,000 families. For 2 liters, 36,000. For 3 liters, 20,000. For 4 liters, 12,000. And 5 liters, 4,000. So the mean value of X as defined in Chapter 10 would be this, right? But that is the same as multiplying the amount of liters times their probability. And in the end, we're going to get 2.2. So that means that we expect on average to see families consuming 2.2 liters of milk. Now, that does not mean that we know what a family will consume, but we can say that that is what we expect to happen. So here's another example with an insurance company that offers to pay you 10,000 euros when your car is damaged beyond repair, or 5,000 euros for major damage. That's 50%. They charge you 50 euros per year for this service. Can they make a profit? Okay, then suppose that 1 out of every 1,000 cars is damaged beyond repair, and another 2 out of 1,000 will have serious damage. So that means that the expected amount the insurance company pays is this average, right? Notice that it's 10,000 times 1 over 1,000 plus 5,000 times 2 over 1,000, and then this would be 0. And this gives us an average of 20 euros per car. So that means that the company is expecting to pay about 20 euros per insured car, but since it's charging 50 euros, it expects to make a profit of 30 euros per car. Now, if they have 1,000 cars, that means that they're expected to pay 10,000 for the first car and 5,000 to each of the other two cars with major damage, for a total expense of 20,000 for all the cars. And then that means that they make 10,000 euros, right? Now, this is not realistic. Normally, they would have to take into account the variance and the standard deviation. So speaking about variance and standard deviation, we have that the formula for computing the standard deviation and the variance of random variables is the same as the one we used in chapter 10. It is important to notice, though, that there's another alternative formula that can be very handy, so I recommend that you memorize it. So now we're going to do example 12.5, which is the last one on this video. And it says a computer store sells a particular type of laptop. The number of laptops sold each day is given in the table. X is the number of laptops sold each day. The store has only 4 laptops left in stock and would like to know how well they are prepared for all eventualities. Find the expected value of the demand as well as the standard deviation. So notice that here we have the table, right? Okay, so they want the expected value of the demand and they want also the standard deviation. So the expected value for the random distribution X is going to be the sum of each X value times the probability, right? So notice that this is simply going to be 0 times 0.08 plus 1 times 0.40 plus 2 times 0.24 and so forth. And this is going to give us 1.90. Then for the standard deviation, we need the variance first, right? So the variance of the random distribution X is equal to, again, the sum of the deviations squared times the probability. So this is going to be and this is going to equal 1.63. Therefore, the standard deviation is going to be the square root of that, which is 1.28. Now, you can also do this with the graphing display calculator, but I leave that to you as an exercise.